Welcome to this explainer. Today we're jumping right into the deep end of the cosmos to unpack what is arguably the most mind-bending phenomenon out there, black holes. We're going to track their entire cosmic life cycle, literally from microscopic relics born right at the dawn of time, all the way up to those hypermassive galactic anchors that, believe it or not, hold entire galaxies together. Let's get right to it. Okay, let's dive into this with a question that might just break your brain a little bit. Are bigger black holes always denser? I mean, the natural assumption is, well, yeah, right? If a black hole is just this point of infinite compression, then surely the absolute biggest, most massive monsters out there have to be the most densely packed objects imaginable, right? Well, not exactly. Check out this comparison. So a stellar mass black hole, one born from a collapsed star, is incredibly dense. It packs the mass of multiple suns into a space roughly the size of a single city. But flip that around and look at a supermassive black hole. These absolute beasts have an event horizon, their physical footprint, that can be the size of our entire solar system. But here's the wild part, the counterintuitive physics. As the mass and the size of that event horizon grow, the average density actually drops. Seriously. If you calculate the average density of some of the largest supermassive black holes based on their immense volume, they're actually less dense than water. Crazy, right? So to understand why they behave so strangely, we gotta quickly look at their anatomy. Right down at the very heart of it is the singularity. This is the predicted center point of infinite density where the laws of physics as we know them just completely break down. Surrounding that singularity is the event horizon. You've probably heard of this one. It's the ultimate boundary of no return, where the gravitational pull gets so ridiculously intense that not even light can escape its grasp. Now, just outside that boundary of no return, you'll often find what's called an accretion disk. Because black holes have this immense, overpowering gravity, they pull in everything nearby, gas, dust, even shredded stars. But this stuff doesn't just drop straight in. It actually swirls around the event horizon at a massive fraction of the speed of light. This creates a superheated vortex that pumps out incredibly powerful X-rays. Actually, this brilliantly glowing disk is very often the only way we can even spot a black hole hiding out there in the dark. And this brilliantly illustrates the sheer scale of what we're dealing with here. Astronomers categorize black holes by their mass, and they use our own sun as the standard yardstick. We call these solar masses. So at the bottom, you've got stellar black holes, ranging from 5 to 100 solar masses. In the middle, the elusive intermediate class, from 100 to 100,000. And at the absolute top, the supermassive titans, sitting at millions to billions of solar masses. We're going to explore all three of these today, plus a bizarre, theoretical fourth kind.
Section 1. Primordial, the tiny relics.
Okay, so we're starting right after the Big Bang. These primordial relics are entirely theoretical, but if they do exist, they were formed in the very first second of the universe. Back then, things were so chaotic and densely packed that pockets of hot material might have just been squeezed tightly enough to collapse directly into black holes. No dying star required. And their mass? It could be incredibly diverse. We're talking anywhere from 100,000 times more massive than the sun to 100,000 times less massive than a paperclip. Just picture that for a second. A black hole the physical size of a single hydrogen atom, but possessing the literal mass of a large mountain. Because they're so tiny and heavy, they could be zipping through the cosmos at enormous speeds, passing straight through stars or even Earth, kind of like a bullet without causing any real damage.
Now, what's really interesting about this is a concept you probably don't associate with black holes at all: evaporation. The legendary physicist Stephen Hawking actually theorized that quantum mechanical processes at the edge of the event horizon cause black holes to emit particles over time. This is known as Hawking radiation. For the big black holes, this process is painstakingly slow. But for these tiny, microscopic primordial black holes, they can actually shrink and eventually evaporate completely over eons. A shrinking black hole. How wild is that?
Section 2. Stellar Death of Stars. All right, moving forward in cosmic time. Unlike those primordial relics, we know exactly how these stellar bad boys form. It is a sequential, step-by-step cosmic tragedy. It starts with a massive star, at least 8 times the mass of our sun, just happily burning through its nuclear fuel. But eventually, the tank runs empty. Without the outward pressure of that nuclear fusion pushing back, gravity just instantly takes over. The core collapses in on itself, rebounds, and creates this spectacularly violent shockwave that we call a supernova.
Now, if the original star was massive enough, say 20 times the mass of our sun or bigger, that core collapses completely, leaving behind a stellar mass black hole. Just take a look at this real-life binary system called Cygnus X1. What you're seeing here is a stellar black hole orbiting a massive blue star. Its gravity is so intense that it's actively pulling or accreting this massive stream of superheated gas right off its doomed neighbor. All that gas gets ripped away and forms a glowing, brilliant accretion disk right before it crosses the event horizon forever. And honestly, tracking those massive X-ray emissions is exactly how we manage to locate these invisible giants in the dark. Section 3. Intermediate. The missing links. So we see stellar black holes capping out around 100 solar masses, and we see the supermassive ones starting up in the hundreds of thousands. But what about the middleweights? Scientists have been actively hunting for this puzzling size gap. I mean, how exactly do you get a black hole that weighs, say, 50,000 suns? Well, the leading theories suggest they're an evolutionary bridge. Over billions of years in tightly packed chaotic star clusters, stellar black holes might literally collide and merge together. Or, another idea is that dense groups of stars collide to form a single, unstable superstar that immediately collapses. They're kind of like the cosmic teenagers, growing steadily over eons, but incredibly hard to catch in the act. Section 4. Supermassive, the galactic anchors. Reaching the zenith of our cosmic life cycle, we have our home, the Milky Way galaxy. For the longest time, pop culture has painted black holes as these terrifying cosmic vacuum cleaners, just wandering the universe and sucking up everything in their path. But we really need to reframe that narrative. Look at how they actually function. Almost every large galaxy out there has a supermassive black hole sitting at its exact center. They aren't destroying the galaxy, they're actually the vital gravitational glue holding the whole thing together. They are the anchors around which hundreds of billions of stars dance.
Let's move to this comparison to see how this builds, because visualizing this is pretty cool. Imagine the fabric of space-time as a tightly stretched rubber sheet. If you place a small marble on it, representing our stellar mass black hole, it creates a very sharp, steep, localized dip. Get too close and you fall in quickly, but from far away, you barely even notice it's there. Now swap that out and drop a massive bowling ball onto the sheet. That's our supermassive black hole. It creates a vast, sweeping, huge depression in that rubber sheet. Its gravitational influence extends incredibly far outward, gently and steadily guiding the orbits of matter, stars, and gas over tens of thousands of light years.
And some of these supermassive bowling balls are just terrifying in scale. To put this in perspective, the anchor of our very own Milky Way, Sagittarius A star, is about 4 million times the mass of our sun. Which sounds huge, right? But way out in the cosmos, anchoring the center of the galaxy Holmberg 15A, sits an ultramassive monster estimated at 40 billion solar masses. Let me repeat that, 40 billion. Our entire solar system could easily fit inside its event horizon with plenty of room to spare. Absolutely mind-blowing. Section 5. Proof and Unsolved Mysteries. So the crucial point here is understanding the line between math and actual observation. On one hand, you have the tiny primordial black holes, which remain purely theoretical. The math absolutely works, the physics allows for them, but 13.8 billion years after the Big Bang, we still have zero definitive proof that they ever existed. But on the other hand, supermassive black holes, those are definitely no longer just a theory. Thanks to the Event Horizon Telescope, which is this incredible interconnected network of observatories all around the globe, we've actually captured direct, high-resolution images of the glowing accretion disks around the black hole in galaxy Messier 87 and our very own Sagittarius A star. We've literally taken a picture of the unseeable. Yet even with these incredible photos, so much remains a mystery. What actually happens to matter when it finally hits the singularity? And if those microscopic primordial black holes really do exist out there, could they be the invisible dark matter that makes up the vast majority of our universe? It seems like the deeper we look into the abyss, the more these cosmic titans challenge our understanding of physics, time, and our entire place in the universe. Thank you so much for joining me on this explainer. Keep wondering.